2, 1. Okay, what's happening, everybody? Welcome back to the part 2 of the section 4. It's 4.2 now, section 4.2 video. In the very first video, or the video I filmed with the class, the Wi-Fi went out, so that recording is, what's the PC word for crap? It's not good. So anyway, I'm going to record a second bit just for you viewers at home, right here with the rest of the class. So let's get going. So the last thing we just did is we proved that the rational numbers are not closed under division. Yes, that's what we did. It's so much weirder without a class here to like interact with. But anyway, we got this. It's okay. I don't need anyone. I can math all alone. So that was the last thing we did. But really, the reason why the rational numbers weren't closed under division was just 0. 0 was the only kind of problem child here, right? Because the issue was that if you take any rational number and divide it by 0, you're going to get something undefined. And undefined is not a rational number, right? It's just literally nothing. It's undefined. It doesn't mean anything. So the thing is, though, what if we just take out 0? So let's first make a definition. So let's see here. I think I used purple. You know what? I'm just following what I did in class. Here we go. So definition. There's 2 I's. Well, I have 3 I's. Oh my God, it's a lot of I's in definition. There we go. Definition. Q with a star is meant to denote the set of all the rational numbers except 0. So exactly the set we're talking about. Just set of rational numbers, take out 0, take out that problem child, it'll be good. So the way you can write this is you can say Q star is all the x that are rationals, so x in the rational numbers, such that x does not equal 0. That's literally how you read this set notation. We'll go through it more in depth, like chapter 6 or some crap like that. But see, now I'm saying the word crap. Now I feel so open and free because there's no one here to call me on it. But anyway, yes. So yeah, crap. The word crap is me being free. Yes. So the point is, this is Q star, all the rational numbers, not 0. And so I'm going to write this. This is all non-zero rational numbers. And I want a curly bracket there, down parentheses. There we go. Then we're going to line it up. So let's get excited. Let's do it. So the point is, yeah, we have the definition here. Why do I want to bring this up? Well, it's cool. Right, and the star thing applies to more than just the rational numbers. We call Z star the set of integers without 0, R asterisk, I guess, the set of real numbers without 0. So that's a common notation. Means that it comes up. But specifically, here's the question. If it is true that the only reason the rationals aren't close under division is because it's 0, what happens if we just simply take out 0? So here's the claim. Q star is closed under division. Ooh. And so Q star is closed under division. What's that mean formally again? What's that actually mean? And I hope, by the way, that we're getting comfortable enough with like quantifiers for all and there exists, that when I say what does the thing mean, it actually helps to see it in quantifiers to really solidify what this concept is saying. Whereas before, it might have helped to see it in English. I hope quantifiers you realize are actually more useful sometimes because they're more concrete, not up for interpretation, really. So the 4 ways to say this is being closed under any operation means that if you take any 2 elements in the set and you put them through the operation, it'll stay in that set. You can't get out of the set by doing that operation. So what I mean is that for all x in Q star, and, for all x in Q, let's not ruin the board here. There you go. For all x in Q star, for all y in Q star, x over y, division stays in Q star. Let's just go ahead and see first of all, if we think this is true, right, let's make an aside here, right? Because the first thing we always do before we prove something is decide what we're trying to prove and why we think is true, right? We need like a proof sketch, like an idea of what we're going to do. So the idea here is if we take any x over y, if x and y are both rational numbers, that will, greater than q star, that means that they're rational numbers that aren't zero. So in particular, x can be written as a over b, and y can be written as c over d, where a, b, c, and d are all integers, and then b does not equal 0, and d does not equal 0. That's what it means to be rational. Okay, so then we know we can divide rationals by flipping and multiplying. So we get d multiply, this is the same as a over b times d over c. And then by fractional multiplication, we get this. So here's the question. Is this in Q star? And here's the time in class where I normally wait for a very long time for someone to muster up the courage to answer. But I don't do that anymore because I know the answer and I have plenty of courage. So the point is, this is unbelievable. So that's what the cowardly lion trying to prove he's cured. I have courage, don't worry about me. I don't need help. Yes, this is AD over BC. The question is it in Q star? And well, what's it mean to be in Q star? That means it's a rational number that's not zero. Well, let's think about this, right? Note, can it be zero? First of all, we can do this in any order. I'm just going to start with the zero part. Can this be zero? Note if AD over BC equals 0, that would imply what? That implies AD equals 0, right? If a fraction is 0, the top must be 0. It's got to be, just if you think about it. And then, yeah, and so if AD equals 0, what that implies is that A equals 0 or D equals 0. Right? That's just how this rolls. The zero product property. What it means is that for anything called fields in math, it's a whole thing of which the rational numbers are one of them. If two numbers multiplied be 0, that means at least one of them is 0. Pretty interesting. The point is we have this property. So A equals 0 or D equals 0. But the problem is, remember, right, that A over B and C over D equal X over Y are in Q star. So if A equals 0, that means A over B, which is X, would equal 0. But X is specifically a non-zero rational number, so it can't be 0. So this couldn't happen. And same thing with D. Actually, D is a little different. D can't be 0 because it's the denominator of a rational number. So by definition, it can't be 0. So we knew that one wasn't 0 already. So that also can't be 0. So AD doesn't equal 0. So the whole thing's not 0. So thus, AD over BC is not equal to 0. Since if it did, that would mean AD equals 0, which means A equals 0, B equals 0, or D equals 0, and both of those can't happen. Okay, so we know it's non-zero, but it's a rational. If it is, if it's a non-zero rational, and then we've kind of shown, okay, it actually is, or the non-zero rationals actually are closed under division. So let's get into it. Well, to be a rational number, all that means is that you're a ratio of integers. Well, heck, this looks like a ratio, right? You have an AD over a BC. And the question is, are those integers? Well, this is just multiplication of two integers, right? Multiplication of two ends. So, end. And same thing here. Multiplication of two ends. So, integer, right? So we've just, so what all this means is that, yeah, this is in fact a rational number because this is the ratio of two integers. Whenever you multiply integers together, you get integers. And since we know A, B, C, D are integers by the definition of rational numbers, where these things come from, A times D, B times C will be integers. So this is a ratio of integers and we're good. The only little subtle thing we have to show here is that remember that rational numbers are ratios of integers where the bottom can't be 0. The denominator must be non-zero. And is BC equal to 0? Well, remember if BC equals 0, that would imply B equals 0 or C equals 0, which for similar arguments above can't happen. So BC can't be 0. Okay, so BC can't be 0 meaning that AD over BC, which equals X over Y, is effective ratio of integers that's non-zero, meaning it's a rational number, it's not zero, so it's in the non-zero rationals. We're talking in circles here. The point is, yes, this looks like it should be closed under division. Okay, my hair is crazy right now, but the point is, and it reflects my inner, it reflects my inside. But the point is my emotional state. But what's the point? Oh yeah, so the point is, this looks like the claim will be true. I say looks like only because we haven't really proven it yet. This is all kind of informal. The whole point of a proof is that we're going to sit down and write down every single detail, make sure there's nothing we missed. All right? If you do a proof correctly, if you do a proof, this sounds stupid. I was going to say if you do a proof correctly, there's no way you can be wrong. But what I mean by that is that if you lay out a proof, you don't skip any steps, you do everything validly, that's a word, right? Then your conclusion must be true, and we can be sure that we're right. I mean, as sure as we are, yeah, I'm just gonna leave it there. I mean, technically, I mean, I guess someone could skip maybe you could overlook a detail in a proof. You don't even know it's like you just kind of forget about it, and then I guess there's a probability that every other human being that looks at it forgets about it. But assuming that human beings, assuming that human beings aren't being deceived by our own brains, then we can be sure. That's really as sure as you can be, right? Forget that part. It doesn't mean anything. The point is, if the proof is valid, we can be sure in our conclusions. So let's make a valid proof. Proof. There it is. Gosh, that was. So we're trying to prove that for all x in the non-zero rationals and for all y in the non-zero rationals, x or y is the non-zero rationals. So we're trying to prove a universal statement about infinitely many things, right? Because there's infinitely many rational numbers, the fractions. And our two ways to do that are method of exhaustion or direct proof. Method of exhaustion, totally out here, right? Because we're trying to prove something about infinitely many things. We don't have that kind of time to prove. We don't have that kind of time to write down infinitely many cases. So to use direct proof. And remember the idea behind direct proof is that you just consider any arbitrary element in the domain and show that the property of those things being in the domain must necessarily lead to the property of what you want, in this case, x or y being q star. If you do that for any old element in the domain, that means it must work for every element in the domain. So what we're going to say is wow, I need to work on my L's, my E's, and my T's apparently. Let's say let x and y be arbitrary but particular elements of q star. And note, by the way, that arbitrary, that just means they're any old elements. Like, you can't assume anything special about them other than the fact that they're in q star. Anything that we assume about x and y should be true for everything in q star. That's the only thing we know about them. But particular means that they are an element. Like, we're going to pick one. We don't know what it is, but it's one. Yeah. And elements, by the way, if we would talk about this, elements is just what you call things in sets. They're called elements. Like how you call people that go to Virginia Tech Hokies, just a name for it, right? Yeah. A great name. But anyway, so blah, blah, blah. Yes, so yeah, this is the setup, right? So x and y are particularly arbitrary elements of q star. And we're trying to prove that just this property of them being q star is going to lead to x over y necessarily also being q star. All right, so let's check out what's the property. What's this give us? Like, what does them being in q star mean? What are some properties of that we can take advantage of? Well, remember, like we said in the scratch work, q star means you're in the rationals non-zero. So, particular, you're a ratio of integers, which you get that whole definition there. And by the way, I'm just going to write down the side here, just so we have it. Q, by definition, is the ratio, any ratio A and B, where A is in Z, B is in Z, and B does not equal 0. All of those guys. All right. So first things first, if you're in q star, thus x and y are in q, and x is not equal 0, and y is not equal 0. right? That's what it means to be a Q star, a rational number that's non-zero. And I'll say, yeah. Then, since X and Y are both elements in Q, by definition of Q, there exists, I was gonna say integers, but I say there exists A, B, C, D, in Z, such that B does not equal 0 and D does not equal 0, such that X equals A over B and Y equals C over D. Right? Because that's what it means to be a rational number. It means that you can be written as a ratio of integers where the bottom, B, and D, or the bottoms or the B's and D's in this case, are not 0. That's a thumbs up to nobody. Hope you're having fun. So yeah, so the point is, this is what it means just to be a rational number. Having the property that you're in Q star means that you must have the property that you can be written like this. But in particular, you're also not 0. Right? So what that means is this will become important later when we start doing our proof, right? It was important to us that A and C don't equal 0. So what this means, so let's note, right? If A would equal 0, then X, which equals A over B, which equals 0 over B, which equals 0, or then X would equal 0, which is not the case. Similarly, I say that word weird, similarly, that's how I spell it, similarly. Similarly, oh, that was my chance to redeem myself and I nailed it. Similarly, if B equals 0, nope, I want C. If C equals 0, then Y, which equals C over D, which equals 0 over D, which equals 0, which is not the case. The point is, right, what we have here, this is actually kind of like, what's going on under the scenes here is, this is modus tollens, right? So what I want to conclude, I'm sorry. So I want to conclude is that if A equals 0, since that if A equals 0, that would mean X equals 0, and we know X isn't equal 0, that must mean A couldn't have been 0 to begin with. So thus, A does not equal 0, and similarly, B is not equal 0. The intuitive idea being that, C, and C is not equal 0. The intuitive idea being, and once again, if C was 0, that means Y is 0. We know by definition of Y being Q star, Y is not 0. So C must not be 0, because it would lead to something we know is not true. And this is exactly what like modus tollens is or contradiction is, right? Because this statement right here, that's saying, this is a true thing, that A equals 0 implies X equals 0. But we know from this statement right here, not X equals 0. Therefore, not A equals 0. Right, we're using modus tollens here, or we could use contradiction, which is the argument that goes, A equals 0 implies false, because it implies X equals 0, which is false. Therefore, not A equals 0. Because it couldn't happen because it would lead to something that's false. Anyway, we don't need to write that. The point is, this happened under the hood. So, yeah. So we know A is not equal to 0 and C is not equal to 0. So we know that A, B, C, D are integers, and they're all non-zero, right? B and D aren't 0 because they're the denominators of a rational number, right, which can't be 0 by definition here. And then A and C can't be 0 because by kind of this modus tollens argument we did under the hood, if they were 0, that will lead to X and Y being 0, which are not by definition. Okay, we got this. I'm sorry. I'm talking in circles because I want to make sure we got it. This really all makes sense. Then, we're basically almost done this. Almost done now. So now, consider X over Y. X over Y equals A over B over C over D by substitution. And then A over B divided by C over D, that's just going to equal A over B times D over C by fractional division. The whole flip and multiply business, right? We're not assuming we know how algebra works, right? Like I can take you through the proof of this, but we don't need to. And then this would just be AD over BC by fractional multiplication. All right. So, what's next? So, sorry about that. So what we've just done is we've shown that X over Y equals AD over BC, just like in our scratch. But now we need to show, what do we show? We're trying to show X over Y is in Q star. So we need to show that AD over BC is in Q star. That's where this is all leading. Now being in Q stars means you're a rational number that's non-zero. So first it starts with the rational number and then show it's non-zero. So to be a rational number, you're a ratio of integers. If we do a ratio here, AD in the numerator, BC in the denominator, so all you need to show is that AD and BC are integers themselves. So I'll say note, since AD, or I'll say A, B, C, D, and Z closed under multiplication as a fact, AD is in Z and BC is in Z. All right, so AD and BC are in fact integers. So to be a rational number, all you have to prove is that AD over BC such that BC, the bottom, the denominator BC is non-zero. Because then we get undefined, that's no good. So this is going to go up here. Further, since B does not equal 0 and C does not equal 0, BC does not equal 0. Thus, X over Y, which equals AD over BC, is in Q, right? Because it's a ratio of integers, AD and BC, and the bottom's on 0. So now we know that X over Y is in Q. We're so freaking close, but we want to show that X over Y is just in Q. We want to show it's in Q star. That proves that Q star is closed under multiplication. So now just being Q star to show that it's non-zero. And being non-zero all depends on AD. So I'll say, finally, note that A does not equal 0 and D does not equal 0. Thus, AD does not equal 0. And so AD over BC does not equal 0. Right? Yeah. I'm comfortable with all this. Yeah, so AD over BC cannot equal 0 because A and D themselves aren't 0. That's the only way you're going to get 0 here. Therefore, x over y, which equals AD over BC, is in Q and not 0. So xy is in Q star by definition of Q star. And put a square on it because we're done, right? All we've shown, so what we've shown here is that for any arbitrary particular x and y you pick, the ratio in Q star, the ratio x over y will be in Q star. And since it works for any old element in Q star, it must work for every old element in Q star, right? So this works for everything, meaning Q star is true. Q star is truly closed under division. No matter what two elements of Q star you pick, their quotients will be also in Q star. Any questions? Sadly, I can't answer, but you can always email me questions with the lecture or anything. My virtual door is always open. I just struck the green marker again. There we go. Virtual door is always open. But that is class, everybody. Good job. I wish I could get further today, but in the live lectures or the live recordings, I kind of got hung up by some technical issues, so couldn't do the third proof I was planning on. So we'll just end it there too for you guys as well, and we'll pick it up on what's that day we have class? Monday. All right. Well, good luck on your test, everybody. It's due. You're probably watching this. Who knows when you're watching this? Maybe you did the test a week ago. Maybe you watched this really early and it's due in like a couple hours, or maybe it was due today. Either way, hope your test went well, and I'll see everybody later. Stop share. Stop recording.